So here's a problem that's going to motivate one more concept in trig, a plane problem. We've got a plane flying horizontally at 1 kilometer altitude at 1 kilometer per minute. I'm trying to make it really simple numbers to emphasize the idea. And it's flying over a camera, and this camera is supposed to automatically track the plane and take pictures of the plane. And so it's got to move, and it's got to know what angle theta to be pointing at. And let's define theta to be the angle from the vertical, because that's going to work out well. And it's going to want to know how to point when as a function of time. So ideally, we'd like to have theta as a function of time. And that's not much harder than what I'm going to show, but let's concentrate on getting theta as a function of x. Suppose I know exactly how far this plane is from a point directly above. If it's directly above, it's pretty clear that theta is going to be 0. But suppose I know that the plane has gone 4 kilometers over. Then what angle should the camera be pointing at? Okay. If we were doing this by a human, it's not that hard to just look where the plane is and point to it. But we want to think of this as like a pre-programmed automated camera. We need to do some math here to do that. Okay. So there's trig here, and it's inverse trig specifically because I've got the lengths of the triangle known. In particular, I've got the opposite and the adjacent to theta known, and I want to know theta. Okay, so as usual, it helps if you don't jump into the inverse trig right away, even if you suspect that that's the key. Write down a fundamental identity, a fundamental definition of a trig function, opposite over adjacent. Okay, so in other words, tan theta is x, but the point is that we are assuming we know x, we know where the thing is, which we will if we know what time it is and we know where it started. That's going to be the next part. And we get theta is inverse tangent of x. Okay, really pretty straightforward. What I want to do is not just get that formula, I want to understand what theta is going to do. I want to predict roughly what the motion of the camera is in broad strokes. And for that, a great way to do that, whenever you want to understand qualitatively what a function looks like, you graph it. I want to understand and predict what the graph of the arctangent function looks like. Oh yeah, I sometimes call it inverse tangent, sometimes we call it arctan. Just synonyms for the same important concept. Okay, so let's make a table, but then we want to think about it. We're going to want to look at it a little bit more qualitatively. Okay, so x here, theta here. And the great thing about making a table of an inverse function to a function that you understand somewhat is it's just the same table with the input and output switched. Okay, so that's a super crucial thing about inverse functions is you switch input with output. It's the whole deal, really. Okay, so what I could really do, usually I look at the inputs first and then I put the corresponding outputs, but I could just cheat and put the outputs and the inputs over here, because these guys are the inputs to the tangent function. Okay, so if theta is 0, for example, x is 0. Oh yeah, that means if I'm pointing straight up, then the thing should be at x equals 0 right above me, because I'm defining this point here to be x equals 0. Okay, if theta equals pi over 4, we know that's the scale setting point for tangent. We know that's really simple. That's 1. Yeah, if there's a 45-degree angle, it's 1 and 1. It's an isosceles right triangle. Oh, if this is minus pi over 4, let's have this be a signed angle so that these guys are positive, and then these guys, if it's pointing in this direction, that'll be negative. So we can keep track of both of those and not have to do them separately. Oh, tangent of minus pi over 4, that's the other scale setting point. Okay. Well, we're starting to get an idea of the graph of this function. Okay, let me see if I can squeeze it in up here. But the trouble is, that's only going to get us so far. And we could start plotting other explicit points, but I want to talk about something smarter than that. Okay, so 0, and so now we're reading it from this direction to this direction. I cheated by thinking of it really as graphing tangent or making a table of tangent, but now I really am remembering that there's a reason I wrote these on the left and these on the right. These are the inputs to the arctangent function. The arctangent, the inverse tangent of 1 is pi over 4. Okay. Pi over 4. And the inverse tangent of minus 1 is minus pi over 4. Okay. Well, I could do other things like pi over 3, pi over 6, and everything like that, but and then I could connect the dots, but there's a better way to do it. There's a better way to think about it, okay? And that is to remember some stuff about general inverse functions. Now I'm going to go to a pretty picture, okay? I'm going to remember that when you have an inverse function, what we can do is we start with the graph of y equals tangent x. And that's presented here in green, okay? And what's supposed to be true about the graph of the inverse function, because of this switch between inputs and outputs, that's a switch between x and y. And what that does is it reflects the graph across the line x equals y. That's the one thing we really have to hold on to in terms of graphs of inverse functions. Okay, so the computer has done that for us with the red line. The claim is that this is the graph of the inverse tangent function. But let's see if we can believe that. First of all, we should check those 3 points we just plotted by hand. 0 goes to 0. Yes. 1 right here goes to, looks like a little less than 1. In fact, about 3/4, about pi over 4. Minus 1 goes to something that's a little above that minus 1. It's really about minus 3 pi over 4. Okay, so it's tracking the 3 points we had already. But let's see what else this graph is claiming. Okay, one of the things that I like to focus on with inverse functions is looking at the features of the original graph and see how they mirrored by features of the inverse graph. In particular, when this guy goes really vertical, that's getting really close to a line that's in the y direction. Well, if you switch y with x, that should correspond to something that's going out very close to being horizontal. So that's an important switch. Let me go back to this guy. When we switch input and output, we switch things like vertical with horizontal. So a good way to check that we really are understanding or we're getting a good inverse graph is that when the original function went vertical, in particular had a vertical asymptote, that automatically is going to create a horizontal asymptote in the graph of the inverse tangent function. Okay, and we'll go back to our actual applied problem to make sure that even in the applied problem that really makes sense too. Similarly, there's a vertical asymptote here, and that's corresponding to a horizontal asymptote out here. The cool thing is that just knowing that actually gives us a good graph. Okay, so let's go back to the by hand picture. Wasn't really using a lot of room. Let's make it bigger, but I don't want to erase my applied picture. Okay, so here's that graph. Here's the graph of the tangent function. Okay, and now here's the graph of inverse tangent. Maybe in another color. Okay, and the claim is it's going like this. Okay. And all we had before on our graph were these 3 points, basically like here. Okay, and it was not clear what to do with that, but all we need to know is connect these 3 dots and then send yourself off on a trajectory towards a horizontal asymptote. And where is it? This was at pi over 2 before we flipped it, and so that corresponds, that was x equals pi over 2, that corresponds to y equals pi over 2. So it's going to have a horizontal asymptote, and at a height we know. And so similarly, this asymptote was at x equals minus pi over 2. That was the tangent function. And so the horizontal asymptote here is going to be at y equals minus pi over 2. So if we just have that kind of S-curve shape, a sideways S-curve shape, not an up and down, and through these 3 points, the central point and the scale setting points, we've got a good graph of inverse tangent. So quick and dirty kind of treatment of the inverse tangent function. Let's take it back to reality though, okay? Do we believe this? Okay, one of the things that's really important here is this horizontal asymptote. Okay, this is x, and then this, in our problem, we weren't calling it y, just our standard like vertical variable. We're emphasizing that that's really an angle. Okay, does it make sense? This says when x gets really, 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 really large, theta should get very, very close to pi over 2, but never quite attain it. That's exactly what the picture says. When the plane goes really, really, really far off to the right, that theta, I'm going to have a lower and lower and lower camera pointing closer to the horizontal. Its angle to the vertical is going to approach 90 degrees for pi over 2. Similarly, way back when, it was looking very, very close to horizontal, way back when the x was very negative. And so this is a weird feature from some perspectives, but it's exactly what has to happen. inverse trig problems very often give you these kinds of cases where in some sort of limiting case, things get interesting. Something goes off to infinity, or something becomes almost vertical or almost horizontal. So in the next one, I'll talk about very briefly about inverse sine. Actually, let's see. I think I'll maybe use my old video on inverse sine because that's a good place to connect.